Kubernetes components. In the world of cloud-native computing, Kubernetes stands as a powerful orchestration system for automating the deployment, scaling, and management of containerized applications. To truly understand how Kubernetes works under the hood, it's important to explore its core components. These components are divided into two main categories: the control plane and the nodes. Each plays a unique role in keeping a Kubernetes cluster functional, efficient, and resilient. Let's begin with the control plane, the brain of the Kubernetes cluster. It's responsible for maintaining the desired state of the system, determining when and where to deploy containers, monitoring the cluster, and reacting to changes in workload or infrastructure. At the heart of the control plane is the kube API server. This is the front end for the Kubernetes control plane, serving as the central hub for all communication within the system. Every interaction with the Kubernetes cluster, whether it comes from the command line, a UI dashboard, or another service, goes through the API server. It's the gatekeeper, validating and processing requests. Working closely with the API server is the etc database. ATT is a lightweight, distributed key value store that acts as the cluster's single source of truth. It stores all the configuration data, current state, and metadata for the cluster. If the API server is the gatekeeper, etc is the memory of the cluster, ensuring state consistency and reliability even in the event of failure. Another vital component is the kube scheduler. Its job is to watch for newly created pods that have no assigned node and then determine the most appropriate node to place each pod. It considers several factors such as resource availability, hardware constraints, policy rules, and affinity requirements. Think of it as a traffic controller, ensuring that workloads are balanced and efficiently placed. Then there's the kube controller manager. This component runs a set of controllers, each responsible for a specific task. For example, the replication controller ensures that the desired number of pod replicas is running at any given time. The node controller monitors the health of the nodes, while the job controller manages job execution. These controllers continuously watch the state of the cluster and make necessary adjustments to match the desired state defined by the user. Finally, we have the cloud controller manager. This component is specific to environments running on cloud platforms. It interacts with the cloud provider's APIs to manage infrastructure-level resources like load balancers, storage volumes, and networking routes. It allows Kubernetes to integrate smoothly with cloud services, maintaining separation between cloud-specific and core Kubernetes logic. Now let's move on to the nodes, the workers that actually run the application containers. Each node has its own set of components. The kubelet is a small but crucial agent that runs on every node. It takes instructions from the control plane, ensures the containers are running as expected, and reports back the node status. The kubelet only cares about containers created through Kubernetes. It won't touch containers started manually. Complementing the kubelet is the container runtime. This is the software responsible for running the actual containers. Kubernetes supports several runtimes like Containered and CRIO. It's this component that pulls images, starts containers, and manages their lifecycle on each node. The third key element on every node is the kube proxy. This component handles networking for the pods, managing IP translation and routing traffic to the correct pod. It ensures that services can communicate both internally and externally, creating a stable and reliable network environment across the entire cluster. Together, these components form a powerful, distributed system. They interact seamlessly, maintaining the desired state of applications and infrastructure. Understanding how these pieces fit together is essential for any developer, engineer, or architect working with Kubernetes. It's not just about deploying containers, it's about orchestrating them intelligently, efficiently, and reliably. Summary: Kubernetes is built on a foundation of modular components that work together to orchestrate containerized applications. At the heart of the system is the control plane, which includes the API server, etc, scheduler, controller manager, and optionally, the cloud controller manager. These components define and manage the overall state of the cluster. On the other side are the worker nodes, each running a kubelet, a container runtime, and the kube proxy and container runtime, software responsible for running containers. These ensure that application containers are running as intended and can communicate effectively. Together, these elements enable Kubernetes to provide a robust, scalable, and resilient environment for modern application deployment. Kubernetes Object Management, Imperative and Declarative Object Configuration. In Kubernetes, everything you manage, whether it's a pod, a deployment, a service, or a config map, is represented as an object. These objects define the desired state of your cluster. They describe what resources should exist, how applications should behave, and how they should interact with each other. But how do you tell Kubernetes what you want? That's where object management comes in, and it comes in two primary flavors: imperative and declarative. Let's start with imperative object configuration. In this approach, you directly issue commands to the Kubernetes cluster using the kubectl command line tool. For example, if you want to create a deployment, you might use a command like kubectl create deployment my app image equals my image latest. When you use imperative commands, you're essentially saying, Kubernetes, do this right now. This is a quick and easy way to manage your cluster when you're experimenting, debugging, or making small one-time changes. Imperative commands are great for speed, but they don't scale well. As your application grows, managing dozens or even hundreds of objects using one-off commands becomes difficult to track and maintain. That's where the declarative approach shines. With declarative object configuration, you define the desired state of your objects in YAML or JSON files. These files describe everything from metadata and specifications to resource requirements and replica counts. Once your configuration is written, you apply it using kubectl apply ffilename.yaml. Kubernetes then works to ensure the cluster matches what you declared in that file. If the actual state drifts, for example, if a pod crashes or a deployment is scaled differently, Kubernetes will automatically reconcile the state to match your declaration. This method is ideal for version control, automation, and collaboration. You can store your configuration files in a Git repository, review changes with your team, and even integrate them into C/CD pipelines. It's a powerful, repeatable way to manage infrastructure as code. There's also a hybrid approach, sometimes referred to as imperative object management using configuration files. Here, you write YAML files just like in declarative mode, but instead of using kubectl apply, you use imperative commands like kubectl create f or kubectl replace f. This still lets you define objects in files, but Kubernetes won't automatically reconcile changes over time unless you manually reapply them. Ultimately, choosing between imperative and declarative management depends on your workflow. If you're quickly prototyping or learning Kubernetes, imperative commands might be all you need. But for production environments, where consistency, scalability, and repeatability matter, the declarative method is the way to go. Summary: Kubernetes objects represent the desired state of your cluster, and you can manage them in two main ways, imperative and declarative. The imperative method involves direct commands through the kubectl CLI, ideal for quick changes and experimentation. Declarative management uses configuration files to describe what the cluster should look like, which Kubernetes then works to maintain. While imperative is fast and flexible, declarative is scalable, maintainable, and well-suited to modern DevOps practices like version control and continuous deployment. Kubernetes object names and IDs. In Kubernetes, clarity and consistency are essential, especially when dealing with large clusters and many moving parts. To help with this, every Kubernetes object is assigned a name and a unique identifier, or UID. These two elements help ensure that every object in the system can be tracked, referenced, and managed reliably. Let's begin with object names. Names are human-readable strings that uniquely identify an object within a namespace. When you create a pod, service, or deployment, you typically provide a name yourself. For example, you might name a pod web server or a deployment backend app. These names make it easier to interact with resources using commands like kubectl get, kubectl describe, or kubectl delete. However, names must follow certain rules. They must be DNS compliant, meaning they can contain lowercase letters, numbers, and dashes, but no uppercase letters or special characters. Also, each name must be unique within its namespace. This ensures there's no ambiguity when performing operations on objects. Now, while names are useful for humans, Kubernetes also relies on something more robust under the hood, the UID, or unique identifier. Every object that gets created is automatically assigned a randomly generated string, a UID, that stays the same for the life of the object. Even if you delete an object and recreate it with the same name, it will have a completely different UID. This helps Kubernetes track the true identity of an object, regardless of any changes to its name or other metadata. The UID is particularly important in situations where resources are short-lived or managed dynamically by controllers. For example, if a replica set is maintaining multiple identical pods, each pod might have a similar name with a unique suffix, but behind the scenes, Kubernetes uses the UID to track each pod individually. Names and UIDs are part of an object's metadata, along with other fields like labels and annotations. These identifiers play a key role in object lifecycle, audit logs, monitoring, and more. It's also worth noting the role of namespaces in this system. Namespaces provide a way to divide cluster resources between users or teams. Within a given namespace, object names must be unique, but the same name can be used across different namespaces. For example, two teams might each have a deployment named frontend, but as long as they are in separate namespaces, Kubernetes treats them as distinct objects. So in short, the name helps users interact with Kubernetes objects in a readable way, while the UID ensures that Kubernetes can always tell objects apart. even when names or other attributes change. In Kubernetes, each object is identified by a name and a unique identifier, or UID. Names are user-defined and must be unique within a namespace, following specific naming rules. UIDs are automatically generated by Kubernetes and ensure each object can be uniquely tracked throughout its lifecycle. Together, names and UIDs allow both humans and the system to manage objects reliably, even in large and complex clusters. In addition to manually assigning names to objects, Kubernetes also provides a handy feature called Generate Name. This is used when you want Kubernetes to create a unique name for an object based on a prefix you provide. Instead of specifying the full name yourself, you set the Generate Name field in the metadata of the object's configuration. For example, let's say you're creating a pod and you set Generate Name, Demo Pod. When the pod is created, Kubernetes might assign it a name like Demo Pod 5C9F8. This generated name is guaranteed to be unique within the namespace. It's especially useful in cases where you're creating multiple resources programmatically or in quick succession, such as in test automation, batch jobs, or temporary resources created by controllers. It's important to note that you can't specify both name and generate name in the same object. It's one or the other. If both fields are provided, Kubernetes will reject the request, and the object won't be created. Also, once an object is created using generate name, the generated name becomes its official name, and you can refer to it like any other named resource. Now let's talk about naming constraints. Names in Kubernetes must follow a DNS label format, particularly for most core resources like pods, services, and deployments. This means names must consist of lowercase alphanumeric characters, or hyphens, must start and end with an alphanumeric character, and must not exceed 253 characters in length. For example, my app01 is valid, while my app, or app_123 would be rejected. These constraints ensure consistency across different environments and systems, including DNS, which Kubernetes uses heavily for internal service discovery. It's also worth noting that some resources, like config maps and secrets, can use slightly more relaxed naming rules, but following the standard DNS-compatible pattern is generally best practice. In short, Kubernetes provides flexible ways to name resources, either explicitly through the name field or dynamically using generate name. Understanding how and when to use each, and keeping within the naming constraints, helps ensure your resources are both valid and manageable. Kubernetes lets you name objects manually or automatically through the Generate Name field, which creates unique names based on a prefix. You can't use both name and generate name together. Resource names must follow DNS style constraints, using lowercase letters, numbers, and hyphens, with a maximum length of 253 characters. By following these rules, you ensure that your objects are valid, consistent, and compatible with Kubernetes internal systems. In Kubernetes, labels and selectors are the backbone of organization and selection. They're how you tag, find, and group resources like pods, services, or deployments. Labels may seem simple at first glance, but they offer powerful ways to manage complex clusters and workflows. Let's unpack how they work. A label is a key value pair attached to an object, such as a pod or service. You might label a pod with app equals frontend, MVF equals production, or tier equals backend. These labels don't have any direct meaning to Kubernetes itself, they're entirely up to you, but they become meaningful when used with selectors. Let's begin with label syntax and character sets. A label key must be a string and can optionally include a prefix. The key format is either just a name, like M, or a fully qualified name like example.com/env. The prefix must be a DNS subdomain and is separated from the name by a slash. Keys can be up to 63 characters long if unqualified, or 253 characters with a DNS prefix. The value of a label must also be a string, up to 63 characters, and it can contain alphanumeric characters, dashes, underscores, and dots. However, it must start and end with an alphanumeric character. So something like production or v1.2.3 is valid, but a value starting with a dot or ending in a dash is not. Now, once you've labeled your objects, you can select them using selectors. There are two types: equality-based selectors and set-based selectors. Equality-based selectors allow you to filter resources by exact match using equals or equals. For instance, MDF equals production selects objects with that exact label, while tier equals frontend selects everything that isn't labeled as frontend. Set-based selectors go further. They let you filter resources where a label's value is in or not in a specified set. For example, you might write any mvin, staging, production, to select objects running in either environment, or use tier noten, frontend, backend, to exclude common service layers. You can also test for the presence of a label key using exists by writing just the key name in a selector, like metadata.labels.tier. These selectors are powerful tools when paired with list and watch operations. List returns all resources that match the selector at the moment of the query, while watch keeps an open connection and streams changes to matching objects over time. This is particularly useful for monitoring and automation, allowing your applications or controllers to react immediately to state changes. Labels and selectors also show up in set references inside API objects. For instance, a service might select pods with app equals myapp, automatically sending traffic to any pods with that label. Similarly, a deployment might use a selector to manage a set of replicas that match its label criteria. These references make Kubernetes dynamic and declarative. Once you've defined your labels, everything else just clicks into place. It's worth noting that not all Kubernetes resources support set-based selectors, but many of the core ones do. Pods, services, replica sets, deployments, and stateful sets all support set-based filtering. However, objects like config maps or secrets typically don't. They're referenced directly by name. Labels aren't static either. You can update them at any time using kubectl label. For example, you might promote a pod from staging to production by running kubectl label pod web server nev equals production overwrite. The overwrite flag is necessary if the label already exists. Changing labels dynamically is a great way to manage rollouts, shifts in responsibility, or group behavior on the fly. Whether you're organizing workloads by environment, version, customer, or team, labels and selectors are foundational. They provide structure and meaning in what could otherwise be a chaotic cloud-native world. Labels in Kubernetes are key-value pairs used to tag and organize resources. They follow strict syntax rules for keys and values, supporting optional DNS prefixes. Selectors, both equality-based and set-based, allow you to filter resources based on labels. Set-based selectors enable more advanced queries like inclusion and exclusion. Many core Kubernetes resources support these selectors, including pods, services, and deployments. List and watch operations use selectors to filter resource streams. Labels can also be dynamically updated to adapt to changing workloads or environments. Together, labels and selectors bring flexibility, control, and clarity to Kubernetes management.